The James Webb Space Telescope has captured the clearest image of interstellar object 3I Atlas. Its chemistry is alien, its path is unbound, and its activity is unlike anything seen before. This is our sharpest look yet at something that came from beyond the solar system. Webb's first look at 3I Atlas. What we saw on August 6, 2025, the James Webb Space Telescope locked onto an interstellar object unlike anything seen before. 3I Atlas, captured using its near-infrared spectrograph NIR spec, Webb delivered not a blur, but a high-resolution image revealing a sharply defined nucleus enveloped in a coma rich with gas and dust. But it was the chemistry that stunned astronomers. The coma wasn't dominated by water as typical for comets. It was overwhelmingly carbon dioxide. Webb measured a CO2 to H2O ratio of nearly 8.1, among the highest ever recorded. This alone reclassified 3I Atlas as chemically exotic. Traces of carbon monoxide, CO, and carbonyl sulfide, OCS, were also found, but water vapor was suppressed, possibly buried beneath dust or shielded within its structure. The directional activity of the emissions made things even stranger. Gas was escaping predominantly toward the sun, hinting at focused outgassing rather than random sublimation. All this at a distance of 3.3 astronomical units, still cold by solar standards, showed that 3I Atlas was active well before typical sublimation thresholds. Thanks to its infrared sensitivity, Webb could distinguish individual emissions, mapping the spatial concentration of CO2, H2O, and dust. What once would have appeared as a hazy speck now revealed textured contours, directional plumes, and fine-scale structure that helped scientists decode both the surface composition and thermal dynamics of the object. This wasn't just a better view. This was a paradigm shift. Webb had turned a transient interstellar comet into a chemical and structural profile permanently archived at the highest clarity ever achieved for an object not from our solar system. And that clarity began raising new, deeper questions. What Webb's instruments uncovered wasn't just surprising. It was unprecedented. While most solar system comets release H2O as their dominant volatile, 3I Atlas released CO2 in massive excess. An 8:1 CO2-H2O ratio is not just uncommon, it challenges the very assumptions behind comet chemistry and formation zones. This suggests 3I Atlas may have formed beyond the CO2 ice line in its home system, a region far colder than the ones that produce typical comets. Alternatively, its subsurface water ice could be buried under a crust, blocking sunlight from triggering sublimation. In either case, the structure or environment was alien to our experience. Webb also detected minor volatiles like carbon monoxide and carbonyl sulfide, providing thermal and radiation history clues. Even possible isotopic signatures such as carbon-13 in CO2 were tentatively identified. Though interpretation is complicated by dust interference, these spectral fingerprints were recorded at precise infrared wavelengths, 4.3 micrometers for CO2 and 2.7 micrometers for H2O. The instrument's resolution allowed astronomers to separate overlapping emissions and track outgassing jets in relation to nucleus orientation and solar angle. This helped them build models for thermal conductivity, layered sublimation, and even rotational dynamics. But perhaps most important was what these findings implied. Either 3I Atlas was born from an entirely different recipe of solar system formation, or the rules of ice sublimation and outgassing that we've relied on for decades are far more variable than expected. Webb's data now enables a comparison between local comets and interstellar ones, and opens the door to testing whether elements like CO2 dominance are galactic norms or local exceptions. The clearest image ever of an interstellar object just became the most chemically rich, and that shifts this story from observation to revolution. Before Webb, interstellar objects were glimpsed in fragments, fuzzy tails, unresolved nuclei, chemical guesses. But now with 3I Atlas, the veil has lifted. What the James Webb Space Telescope delivered wasn't just a photo. It was a microscopic scan of a ghost from another star system. The image revealed a nucleus sharper than ever, encased in an asymmetrical coma glowing with thermal emissions. Its dust structure and gas plumes mapped in striking clarity. Infrared capabilities made this possible. Unlike visible light telescopes, Webb peers into wavelengths that detect heat, molecular vibration, and chemical fingerprints. Its sensors picked up distinct zones within the coma, pockets where CO2 emission peaked, regions where dust was denser, and shadows where H2O trailed behind, all from over 3.3 astronomical units away. And at that distance, it's still cold. Too cold for standard comet models to fully explain such activity. What stunned researchers were the coma's asymmetries. Gas and dust weren't distributed uniformly. The side facing the sun showed bright plumes, while the opposite remained subdued. These irregularities weren't just aesthetic quirks. They hinted at an internal structure that varied dramatically, maybe even surface vents or compositional zoning deep within the nucleus. The boundary between nucleus and coma was also more defined than expected. Instead of blending gradually, Webb's resolution revealed a clear transition zone, likely shaped by localized sublimation or sudden exposure of volatiles. This structure challenged assumptions that coma formation is always gradual and symmetrical. Crucially, the signal-to-noise ratio remained high despite the faintness of the object and its great distance. That alone is a testament to Webb's engineering, and it ensured that even subtle fluctuations in brightness, spectral lines, and jet activity could be tracked with confidence. In practical terms, Webb turned what was once a mystery streak on a sky chart into a chemical map with measurable dimensions. And in doing so, it shifted the discussion from what is this thing to where did it come from, and why does it act so differently from everything we know? While its structure tells us what it's made of, its motion tells us where it doesn't belong. From the moment 3 Atlas entered detection range, it stood out, not because of brightness but because of its path. This was no looping comet bound to the sun. Its orbit was hyperbolic, its eccentricity well over 1, which means it's not part of our solar system, and never was. Traveling at over 130,000 mph, 3 Atlas is slicing through the solar system at an angle of just 5 degrees above the ecliptic plane, but moving retrograde against the direction of planetary motion. This specific trajectory is rare. Most interstellar objects arrive at steeper inclinations, diving in from above or below. But 3 Atlas approached almost edge-on, as if choosing a path that passes close to multiple planets, and it will. Its projected path takes it near Mars in October, skims past Venus, crosses near Earth's orbital plane, and then swings by Jupiter before being ejected back into deep space. That sequence of encounters, not impacting but aligning, is statistically improbable for a random object. It's not enough to prove intent, but it raises flags in orbital models. Simulations showed that the odds of an interstellar body passing that close to 3 major planets in a row by chance are less than 1 in 20,000, and the surprises didn't end with its course. As Webb tracked it, subtle deviations in its speed and direction began to emerge, shifts too smooth to be gravitational alone. These changes matched the orientation of its CO2 plume, suggesting that outgassing might be exerting thrust, a phenomenon known in cometary science, but rarely this measurable. This directional movement, coupled with a stable sunward-facing jet, suggested more than sublimation. It hinted at controlled acceleration. Webb wasn't just observing a fast-moving rock. It was watching a body that appeared to adjust its trajectory as it went. The story of 3 Atlas's journey isn't just about origin and destination. It's about interaction. It is passing through our solar system, not tumbling aimlessly, but navigating with surprising precision, giving us only a short window to observe, study, and understand it before it vanishes forever into the darkness from which it came.